naught L4 over 6. I think I probably had something wrong. Hold on, people. X4 is over 6. BYL cube. There's something wrong with this equation. I'm going to check this. I think I might make a mistake. Okay, hold on. I might make a small, not a small, a mistake somewhere. I'm checking now. Y. So EIY is minus, this is correct. X squared over 6 is correct. I have made an integration error somewhere. 2, this is correct. 12, this is correct. 6, this is correct. 120 is correct. Somehow when I substitute, something is wrong down here. 120L, 12, 2, 6, 6, 6, 6, 12, 6, 6, 2, 12, 120, 6, 6, 2, 12, 120. Okay, I'm still going to do the calculation again. Okay, I'm going to add up the value. Maybe I add up wrongly. So it's 1 minus 1 over 120 plus by 1 over 12 plus by half. So this is equal to, I'm still not getting the same answer. So hold
on. Y by half, wouldn't it be 1 over 6? Because that's what you're adding, right? 1 over 120 W omega naught L4 plus.
So minus 1 over 120. Yeah, maybe I pressed my calculator wrongly. Plus by 1 over 12.
Minus 1 over 6.
Yes, minus 1 over 6. Thank you. Okay. So I did not. So this is 0. It's trying to skip step. That's my problem. Minus 1 over 120.
I want my pint of beer.
Hey?
I want my pint of beer.
Okay, you get a pint of beer without coronavirus. So minus 1/6 plus by thank you. Okay, so this is positive by L cube over 3. Okay, so from here, finally, we can find our by is equal to minus a positive 11 over 40 omega naught L. Okay, so let me not skip step. Okay, if I start skipping step, you get lost, I get lost, everyone not happy. Okay, so this is by L cube over 3 is equal to 11 over 120 omega naught L4. So you can cancel, you bring this over, this left 40, so therefore by is equal to 11 over 40 omega naught L. And the fact is positive means the force is going up. Okay, right. So this is how we solve, okay, statically indeterminate structure. Okay, now I'm going to show you, okay, very shortly, okay, very short example on how to use this technique for a point load with a distribution load. Okay, so I'm going to do a very short example. Okay, bear with me, and I think this is important because so far what we have done is always with distributed load. Okay, and I'm going now is like 11:50. I might go over by 5 minutes if you don't mind. Okay, or less. I don't think I need to. I will go over. Okay, so let's say now. Okay, so this is example 2. 2 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 example 2. I cannot remember which example we are now at. So this is example number 4. Okay. So point load, point and distributed load. Okay. So what if now we have both of them, point load and distributed load? So a typical example, you guys have seen, probably have done this in your homework. What if our structure now is like this? Okay. So we have, this is our point A, our point B. Okay, there is our point. No, that is not a point B. Just I know where's my point A. Then we have evenly distributed load from here to here. Okay, so this is our point B, point C, and our point D. Okay, and the distance from here to here is A, right? You guys have seen this example before, or from your homework, I think. A, and then this will be your L, right? And this is omega, right? And the distance from here to here is equal to L minus 2A, right? So the unique thing about this problem is this: A to B has no distributed load, right? Let's look into into the analysis now. Okay, let's look into the analysis now. All right, let's do the analysis. So the interesting thing is this: between A to B and C to D, right? Omega as a function of x is equal to what? 0, right? I.e., there is no distributed load, right? There's no distributed. So what do you do from here? Okay, so this problem, so we know that AY is equal to DY. Okay, so AY is over here and DY is over here, right? DY is over here, right? So AY and DY, so AY equal to DY, and that is, and based on symmetrical loading and geometry, right? AY is equal to omega L minus 2A divided by 2. Okay, so each side will take the load evenly. Okay, so remember I'm going to do like sections. Okay, let's suppose we go sections. Okay, like before. So A, okay, I'm going to do A to B, because A to B is unique now. It's without a distribute, and I want to show you how to work with this without a distributed load. Okay, then point B, and then B to C, you have a distributed load. Okay, I will not go any further. Okay, because it's very repetitive. So this is by using integration method. Okay, so we know from here. Okay, so the limits. So we know that this is 0, 0, x, and a, right? This is at exactly at length a. This a, x, x, L minus a. Okay, so we're going to form the shear force and bending moment equation. Right. So now I want you all to see this now. Okay, now I'm going to zoom out a bit so when I write you can see. Okay. More. I think you guys can still see this. Right. Okay. So now I'm going to write at A, when x is equal to 0. So you look at point A, right? dv by dx is equal to minus omega as a function of x. Now, the question is this. Is there any distributed load? The answer is no, right? So this function is equal to what? 0. Okay, so now, right? So we have what? VA. So V at point A, right, is equal to V when x is equal to 0, right? This is equal to 0. And V at point A, we found out is equal to what? Omega L minus 2A over 2. Okay, because this value over here, AY, is your what? Shear force at point A. Okay, so now we have V as a function of x. Okay, omega L minus 2A, and then divide by 2. Okay, and then the next thing we know that moment about point A, right? Now remember, this over here is a what? Is a constant. Okay, those over there, that is a constant. So you're telling me, okay, Eugene, let's find moment about point A. Okay, moment about point A is you integrate between 0 and 0, right? And then it's equal to omega L minus 2A divided by 2 dx. Yeah, you can integrate this. Am I right or wrong? Right? You can integrate this. When you integrate this, it's equal to L, omega L minus, come on, omega L minus 2A divided by 2 multiplied by x. The limits is 0 to 0. So this is equal to what? 0. Okay, so now we found our moment as a function of x already. Can you see this can also be done for what? For point load, right? So m as a function of x. So this is 0. Now let's go from A to B. Okay, from A to...
Sorry, why is dv over dx equal to 0?
Huh?
At the beginning, it says dv over dx, which is equal to omega x. It's equal
why do you, then I'll ask you, why do you think it's not equal to 0? What is omega x? It's a distributed load equation, right?
Right.
So from point A to point B, is there any distributed load?
No. Oh,
there you go. Okay. You're not reading, you know. You owe me a pint of orange juice now.
Okay, I'll pay you back.
Okay, you get what I mean? There is no distributed load. That's why students or a lot of, not just students, a lot of engineers thought that this technique cannot be used for point load. It can be used for point load. Mathematically, it's still valid, right? So now let's do from point A to point B. Okay, so let's do from I'm going to do on the side of the page. Okay, so let's do from, I'm going to divide this page. So yeah. So because you can see better. Okay, so now let's do this between point A to B. Okay, so let me see, can you write? So from point A to point B now, right? Then again from point A to point B, right? From point A to point B, so you have dv by dx is equal to minus omega as a function of x. Again, this is equal to what? This is equal to 0. So when you write this out, it is v as a function of x minus by VA, like what we've written since the morning of our lecture, since we started. This is equal to 0 as a function of x, 0, and then this is what? dx, right? And when there's nothing, when there's 0, you integrate is 0. Okay, so this is Vx, V as a function of x, minus by VA. Now you guys will know this better than me. This is equal to 0. So V as a function of x is equal to V at point A, And we know the V at point A from our previous analysis, right? So from our analysis over here, V at point A is equal to omega L minus 2A